So, welcome back students. We are basically discussing functional group based strategies, and we are mainly focusing on several protecting groups and how these protecting groups can be selectively protected as well as deprotected. Now, this particular week we will be talking about some example where you will find that how you can use couple of protecting groups for doing some synthetic transformation. The first problem which I am giving, a starting material was given to you, and the target which was desired is having this structure. Now, if you see the starting material and the target and do a close analysis in a retrosynthetic way, you will find that only thing is the left hand side, this olefinic bond needs to be reformed. Basically, two of the methyl groups have been removed in place of a alpha beta unsaturated ester. This is the target molecule. So, what I now do? We will try to do a retro by remaining all things intact. We are saying that this retro will be doing by keeping this bond by using a CH2 CH2 CHO. By using a Wittig reaction. So, if you have a Wittig kind of reaction, you can basically easily can do it. Now, correlate this to compound. The starting material is this. So, if you are doing a oxidative cleavage of this double bond, you can easily cleave it. Now, if you have this compound is what? This compound is a keto as well as aldehyde, keto and aldehyde. You are saying that this keto and aldehyde, you want to do a Wittig reaction to prepare this alpha beta unsaturated double bond, means that your keto or aldehyde both are basically will undergo Wittig reaction. So, though aldehyde reacts very faster compared to keto, but the ketone needs to be protected. So, now based on this strategy, we will formulate how we can proceed. So, initially the ketone group will be protected. The ketone group can be best protected by ethylene glycol in presence of little bit of acid. So, this ketone is now protected as it is cyclic ketal, okay, is protected. Then you do the ozonolysis. So, ozonolysis means you get the oxidative cleavage here. So, what will get? You get this corresponding aldehyde, then your remaining part of the molecule will be same as it is. Now, you are almost close. Now, you do the Wittig reaction. And then you see the Wittig reaction will be now working on here, and then once the Wittig reaction was done, you just remove this ketal to come back to your target molecule. So, it is basically a just functional group protection, do the FGI, then protection group removal. So, that is why the protecting group also can act as a very good functional group, and you need to take care of this particular protecting group in your synthetic planning. Next particular example we will be discussing the cyclic molecule, and the structure of the starting material which was given is this starting material. The target which I am now drawing is having something like this kind of structure. Now, if you see the target and try to analyze with this starting material, you will find that basically you need to do a new carbon carbon bond formation here, as well as this CH2OH, there also you need to do a carbon carbon bond forming reaction. So, one is here, one is here. So, means that you basically you can think about the carbon carbon bond forming reaction by a standard Wittig reaction. So, you are having a carbonyl is already there and you are having a CH2OH. Now, if you initially do a oxidation kind of thing on this primary alcohol without protecting it, you will basically get a ketoaldehyde. Now, ketoaldehyde, then you have a difficult scenario, because the Wittig insertion of this particular groups are different. One case you need a simple methylene, one case you need a alpha beta unsaturated ketone. So, basically you have to rely on protecting group. Now, this alcohol can be protected by numerous protection group. Numerous protecting group, you can use TBS chloride as the simple protecting group and imidazole. In principle, as I said, any other protecting groups you can also use. So, that will basically give you the corresponding silyl ether. Now, this silyl ether is now you are having a ketone. You do the 1 carbon Wittig reaction, 1 carbon Wittig transformation, that will basically give you the exocyclic methylene group. And now, once the exocyclic methylene group is there, you now next see that what you need to do next. Next, basically you need to do the deprotection of the silyl group, because you need to do another carbon carbon bond forming reaction at this particular carbon. So, F minus will remove this TBS, then you do a oxidation by PCC, then basically you will be end up in this compound CHO. Now, everything is almost set. You can do a Wittig reaction, even you can do a aldol kind of reaction also, but as we discussed about Wittig reaction, let us talk about a Wittig reaction. With the ylite, you can easily prepare from triphenyl phosphine and monobromo acetone and use a base to complete the synthesis in a very effective way. The only thing is you have to use this protecting group of this alcohol. So, this free alcohol needs to be protected prior to the initial Wittig reaction. So, this kind of selective protection and deprotection is a very useful strategy for making a medium sized target as well as complex target. The next target, which will be now discussing, our next problem, basically a starting material was given, the tetrahydropyran based compound starting material was given. The target molecule which was required is having 2 CH2 and this part is the OH. So, basically you need a homologation at this particular primary hydroxy things, you need a 2 CH2. Now, you will find this compound is having 2 hydroxy, primary as well as hydroxy, and you need to do a selective FGI at the primary hydroxy thing. So, basically you need to protect the secondary in presence of primary, but that was often bit difficult, So, what I will suggest, you do it in this way, you take a first a TBS chloride 1 equivalent, okay, and then basically that will give you the primary which is sterically less congested, will first protect it. Okay. The secondary, now you touch, the secondary you can touch or you can protect by different protecting groups. You can use silicon protecting groups like tertiary butyl diphenyl silyl, which will not be affected when you do the acid mediated deprotection of TBS, but let us say do a other chemistry, you do a mom chloride protection. Mom chloride you use DPA. So, now this secondary is now protected as this mom, and this one is now OTBS. So, now as the synthetic strategy requires, you need to deblock this particular TBS protecting group, as you need to have a FGI here. So, fluoride minus is the best thing, that will basically remove the silyl, and it will give you CH2OH. Now, as you need to do a 1 carbon extension, the best reaction is basically a hydroboration reaction. So, for that you need to oxidize it first to convert the primary hydroxy to corresponding aldehyde. The mom protection remains same. Now, aldehyde is subjected to next Wittig 1 carbon Wittig reaction, very straightforward reaction. Okay. So, we are basically close. So, 1 carbon extension was almost done. Now, you do a hydroboration reaction, BH3 THF sodium hydroxide. Once you do the hydroboration, you basically get CH2OH, and this mom is there. Now, you try to remove this mom group by some acid catalyst, and that will basically give you the your target molecule. So, in this way, just by using selective protection and deprotection, you can basically play with the target molecule and try to correlate with the starting material, that how the starting material can selectively be used or can functionally manipulated to the given target. The next couple of problems we have similar kind of scenario, but what I will try to do, I will ask your opinion that how this functional group transformations can be effectively carried out, and what do you think about the entire pathway. We have a compound something like this. The stereochemistry portion I have not mentioned here. The compound structure is this, and I said if this compound, I will be giving you a reagent lithium aluminum hydride, other reagents I am saying that I will at present I am not going to give you, and your target molecule is, see the target molecule which is requested to synthesized is having structure this. Now, if you now closely analyze, the starting material is this which was supplied to you, the target was sought that this molecule you have to make by using a lithium aluminum hydride reduction I have given you. Okay. Now, if you see this compound contains starting material contains a ketone as well as a lactone or cyclic ester. Now, if you now subject this compound, the starting material itself with LH, lactone will definitely be reduced to give you the diol as desired. At the same time, the ketone will be also reduced, but which is essentially not required. So, means that here initially the ketone groups needs to be protected. Now, ketone group protection, as all of us are familiar, you can do a 1,2 ethylene glycol protection, or even you can do a 1,2 thiol protection. So, depending on the availability of the reagent, you can basically protect this to thiol or corresponding oxygen analog. The other part of this molecule will remain similar. Now, as the ketone has been protected, now the ketone is basically its reactivity has been suppressed. Now, you have subject it to lithium aluminum hydride. Now, see this lactone will be reduced, as LH is very strong reducing agent, and then you will basically get this diol, which is the diol core functionality was present in the target molecule. The protecting group remains same, okay. And then if you just remove the protecting group by acidic workup, you will basically end up with this final product. So, this kind of strategy which basically gives you idea that where and which point you need to use the protecting group. It is basically tricky, but you need to be very careful when you do such kind of exercise. The next one will be on similar thought. We will be basically talking about a cyclic molecule, and we say the cyclic molecule structure is this. Okay. Starting material was this. The target which was needed or which we need to synthesize from this molecule is a double bond, does not matter. Okay. And then the target which basically you need to make is this ketone. The starting material, if you see the starting material is having a ketone and a hydroxy group. The final target, the ketone has been deoxygenated, or basically is a kind of redundant functionality, and then this end of this molecule is now oxidized, this hydroxy group is oxidized. So, basically you need to do two reactions, you need to selectively do a deoxygenation here, as you need to do a oxygenation or oxidation particularly at this carbon. Now, let us initially try that what kind of reaction you can think about. Now, in principle if you first oxidize this molecule with a suitable oxidizing agent, that will give you diketone. Now, once the diketone has been generated, you have a difficulties for selective deoxygenation of diketones, because this end this ketone you need to be deoxygenated. So, basically at the very beginning you protect with this OH group, let us say protect with mom chloride and a base DIPA. So, initial protection, all the structural features of the remaining part will be similar, you protect with OMOM. Okay. And then this ketone needs to be deoxygenated, the standard reduction like Wolff-Kishner. So, basically you treat with hydrogen hydrate, this transformation we have already discussed many times, and Wolff-Kishner will basically deoxygenate the carbonyl group and you can get this intermediate without any difficulties. Now, what you need to do? Basically need to remove this mom group. So, which can be clipped by a simple acidic workup, and then you just oxidize it with a suitable oxidizing agent like pyridinium chlorochromate, and then you will find that you will basically end up with this particular target molecule which was desired. So, there are two simple functional groups are there, and we basically protect this hydroxy group with this mom first, do the FGI here, and then remove the mom protection group, and then you oxidize to achieve the target. This was the very simple demonstration of a protecting group chemistry. So, we will try to have more problem which you also can be fitted in the same line. The compound is basically having a bicyclic bridged bicycles and then as a 1,3 diol, as a 1,3 diol. Now, if the target this is starting material which was given to you, the target molecule which was required at this stage, you put a double bond here. Yes. If you see the close structural viewpoints of this target and do a skeleton analysis, skeleton based analysis, you find that if you just simply do a elimination here, that will give you the required double bond. Elimination can only takes place here because there is no hydrogen. Okay. Even hydrogen is also there, the elimination won't takes place because that will give you a double bond in the bridged position, which is violating the Braid's rule. So, now there are two hydroxys, one is tertiary, one is primary. Now, if you directly try to eliminate this compound, this primary OH is also undergoing elimination is because there are hydrogens which can be easily abstracted. So, means that this primary hydroxy group is selectively protected. Now, say if you are having a primary, secondary, tertiary, primary hydroxy groups are sterically less hindered. So, you have a efficiently you can block or you can protect the primary hydroxy group. So, the best way you can just now protect with, let us say is a bulky protecting group is a TBDPS Cl, one equivalent definitely, and then what you will be having? You will basically having this is your OH and this is your CH2CH2 or TBDPS. Now, this tertiary alcohol you need to touch. First convert this tertiary to corresponding mesylate, which will basically give you the mesylate derivatives, because mesylate derivatives are easy to be eliminated, right. Convert to O mesylate and then you heat with a base, suitable base. This undergoes E2 elimination and there basically you will find the olefin, this olefin. Now, this olefin, and if you analyze this target are basically very close, only thing is you need to remove this TBDPS, that you can easily do by treating with tetrabutyl ammonium fluoride, which is a nice fluoride source, you can get your target molecule. So, based on the structure of this particular product which was desired, you can efficiently design a pathway which will be very useful and very much valuable. We will try to stop our discussion just by talking about this example, and let us see this example is a bicyclic ketone, but there are two carbonyl functionality, one is alpha beta unsaturated, one is saturated. Okay. And then the target molecule which was given here, is something like this. So, this is starting material, the target. Now, see the starting material and target, we basically find that only reaction which we need to do just a Wittig kind of reaction. Now, if you simply do a Wittig reaction on this target, the saturated ketone might react faster, because saturated ketone is obviously very much reactive. Saturated ketone, this ketone needs to be protected at the very beginning, that is why. So, first use a simple ethylene glycol, which will basically protect or block your saturated counterpart. Saturated ketone portion will be basically blocked, and then you see next what it can be done. Next, basically what you need to do, you basically need to do a Wittig reaction with the help of a simple Wittig elite. Now, this Wittig elite can be efficiently generated with the help of pH3P plus ETI minus. So, triphenyl phosphine and ethyl iodide can simply be mixed together and you get this corresponding elite. Now, this elite, when you react with a base at the beginning, you basically get the, this is basically salt, you basically get the corresponding elide here, okay. And then do the Wittig reaction, which will basically now give you the double bond geometry I have not mentioned here, and then this ketal will be as it is. Now, if you see, you need to deblock the ketal. You need to deblock the ketal means you just react with H3O plus acetic workup, which will remove the ketal. I say ketal deprotection. So, ketal group is now deprotected, and definitely you can end up with the final target molecule. So, only thing is the two starting material having a virtually rate differences for the initial protection. Saturated carbonyl compound and unsaturated carbonyl compound. Saturated carbonyl compound is much more reactive, because for unsaturated carbonyl compound the electronic nature is little bit different due to this particular resonance. Okay. For this compound, it will react faster with this ethylene glycol, and it will give you the cyclic ketal. So, this reactivity is suppressed, then you do the Wittig reaction with this reagent and you will end up with this particular target molecule. So, similar kind of problems basically can be tackled with relatively easier functional group operation, and you need to just use selective protection and deprotection group chemistry. So, protection group chemistry probably we can conclude, and so guideline 4 in the functional group based strategies we have covered, and try to remember there will be couple of assignments when you talk about the more protection group chemistries, and so you have to go through the assignments and please try to solve those assignments. Until then, goodbye, have a good time.